Alright, CNT120, Chapter 6. We're now moving on to the section on antennas. Similar as with wired, when we talk wireless and wired, similarities, layer 3 and above, were the same. IP, TCP, UDP protocols, all that good stuff. Wired and wireless networks are the same. Where we're different is at layer 1 and 2, when we're dealing with a wired network. Wired network, we have an electrical pulse of electricity, representing the ones and zeros, a pulse of electricity for 1, no pulse for 0, that's going across a copper conductor, if you will. If it is a fiber optic cable, it's a pulse of light going across that glass fiber. Pulse of light for 1, no pulse for 0. Now, when I move into wireless, the difference is I no longer have this fixed path that I can send a signal across. It is a radio frequency going through the air. There's no fixed path. So I need an antenna to transmit as well as to receive my signal. And the same frequency is required on each antenna when I'm sending and receiving. I have to be in the same channel, if you will. If I'm sending at 2.4 gigahertz, the other receiving end needs to be in that 2.4 gigahertz frequency band, if you will, to receive that. Now, with antennas, we have what are called radiation patterns. Different antenna designs are designed to send a signal out in different ways. We have directional and omnidirectional antennas. Directional is a focused antenna. You can almost think of it as like a dish. It is focusing the energy in more of a beam from A to B. This is the kind of thing that would be like satellite TV antenna if you have a dish outside. The signal coming from the satellite is kind of emanating down to you, and as long as you have the dish faced in the right direction, it will pick up that signal for your television signal. That is a directional antenna. Meanwhile, there are omnidirectional antennas, and it broadcasts in all directions. A lot of your wireless access points, if you think back to the ones that used to have the little antenna sticking up, they were designed to broadcast in all directions. That way you could be sitting in the living room, bedroom, dining room, and pick up the signal all around your house, if you will. My access points a lot of times are like that, as well as things like TV and radio stations. When they're broadcasting out their signal through the air, it's broadcasting out in all directions, omnidirectional. So as I look at different antenna styles, they have different functions. They could be focusing the energy in one direction, or they could be trying to broadcast out in all directions. So as I have different wireless antennas, I want to be aware of its radiation pattern. Here would be a omnidirectional antenna. This would be an omnidirectional antenna right here, where the broadcasting is kind of going out. Almost looks like a squashed ball, but it's going out in all directions around the antenna. Something like your access point at home. A lot of us had an access point that looked like this at one point or another. This dipole antenna is broadcasting out like so, almost like a squashed ball. So if I put it kind of in a center room of my house, all the rooms around it, above and below it, should be able to pick up that signal. That's the idea behind that style of antenna. Meanwhile, if I have an antenna like this is what's called a Yagi antenna. That is designed to focus the energy almost into a beam. So if I were back here, I probably would not pick up the signal at all. If I'm out in this direction, I definitely would. That is a focused antenna called a Yagi antenna. Fun side note, there are all kinds of plans out there for people to take a ordinary wireless like dipole antenna and convert it into a directional antenna using things like a soup can or a Pringle can, and that takes that omnidirectional radiation pattern and tries to focus it more into a directional pattern. And believe it or not, these things work, especially the Pringle can. You do need to do a little bit of math. You can't just kind of poke this through anywhere. You look at the frequency and the size of your wavelength, then it decides how far forward or back you put this. And then this Pringle can, that you have the metal disc in the bottom, on the inside is foil. All of that is focusing it out in this type of direction. And you can actually make two of these and connect, one house to another house with these two directional can antennas. It does work. It's pretty cool. So when I'm dealing with antennas, I think about range. What kind of geographical area can I get with a particular antenna? And directional can extend that range, and I might see these kind of things giving me that directional antenna to go from a building out to maybe a booth in the middle of the parking lot for the gas pumps. You might have a directional antenna connecting those two together. Just giving you an idea where you might see that kind of thing. When you're dealing with antennas, there is actually a measurement, received signal strength indicator, measures the power of the signal on the receiver's end. So how much of the signal is getting to the receiver, like my laptop, if you will. And that is measured in decibels relative to 1 milliwatt. That's what the dBm is. And typically shown as negative. Remember, close to 0 is better. And I think they give you a couple breakdowns here to give you an idea. Negative 30 decibels per milliwatt is really good. I have a really strong signal. As that number gets larger, the signal is getting weaker. I might be further away, or the signal is getting weaker, and gets to a point where it's like okay or really bad. Now, a lot of us look at our icons on either our laptop, and we see the bars, and it gets less and less and less. We'll think about this would be all the bars, and down here would be none of the bars. And that could be on your laptop or even on your cell phone for that matter, or tablet or whatever you're using. So you would have all the bars here and pretty much none of the bars there. That's what we're kind of getting at with this measurement here. Signal propagation talks about how the wave travels from one point to another. A lot of our wireless signals are line of sight, meaning I need to be able to see transmitter to receiver for that to work. I'm not saying it doesn't mean I can't broadcast through a wall or something, but for really good signals, it's usually line of sight, if you will. Directional antennas can achieve this, but obstacles can affect our ability to transmit. Now, I put this in as a quick example. A lot of us have seen this at one point or another. You'll see a van alongside the road with this boom that goes up. This is usually this is a microwave link, but it's a directional antenna. Well, that television live truck, if you will, that broadcast here, that microwave broadcast here usually goes to a tower up on a mountain nearby, and that might relay the signal back to the actual television station. I purposely used this one here. This is WITF. That's the public TV in the Harrisburg area. So if you have a live truck out in, let's say, York, as long as you can hit a tower on one of the mountains nearby, you can relay it to Harrisburg. So as long as I have kind of like a line of sight from the truck to a relay tower on a mountain, and then that has line of sight back to the television studio, I can get the signal back there. That's what they mean by this line of sight thing. A lot of our wireless signals like that are line of sight. Now, when I'm talking Wi-Fi and so forth, I can be broadcasting through walls, but things are going to affect my signal, which gets to this. Obstacles affecting my signal travel. Signals may pass through an object, they might be absorbed, or might be subject to some phenomenon. So ideally, if I have line of sight, I have the best possible send to receive ratio, if you will, sending my signal and receiving it. But as I add more obstacles and more distance, all of those things are going to affect my signal. So let's take a look at these different phenomena. I tried to put some examples in here to help you sort them out. So naturally, when you send a signal, it's going to weaken. Even if we have like a perfectly wide open field, antenna on one end, my laptop on the other end, if you will, no matter what, the further the signal gets away from the antenna, it's going to weaken. That's just natural. And that's what they mean by attenuation. It's going to weaken as it moves from the transmitter out to the receiver, if you will, out to the laptop, if you will. It can be subject to fading as it goes through objects, and we could be talking just leaves on a tree, okay? But as it goes through maybe a drywall wall in your house or a brick wall in the house, some materials the signal will go through pretty well. Others, it's going to weaken tremendously. And I think they use the example here of a brick wall versus like a concrete block wall with the reinforced mesh on the inside. That's going to weaken it significantly. I can be subject to interference. There are plenty of things that are broadcasting in our wireless bands now. And I grabbed this sample offline, but this would be, if you use a Wi-Fi analyzer and wherever you live, if you live in a neighborhood, you're going to end up seeing this. You're going to see a ton of SSIDs on different channels in different channels in on your frequency band. These could be all of your neighbors. Well, if I'm trying to use this channel here, I have a lot of neighbors with the same channel that might be interfering. That happened at one point in our house where my wife told me one day when I got home, she's like, hey, when the dishwasher and the dryer are on, I lose my wireless signal. And here what it amounted to is I used a Wi-Fi analyzer and found out all the neighbors were on channel 6. We were on channel 6. And when we turned things like the dryer and dishwasher on, that was enough extra noise that the interference that we had before, this noise now drowned it out and we would lose connection, if you will. So once I moved it to, I think I moved it down to like channel 1 where there are less people, that issue went away. So things like interference from neighbors, other devices around, could be affecting your signal. It could be subject to refraction. Refraction is the bending of. As the signal goes through a device or through a material substance, it could bend. In some cases, it might bend in a positive way. Going through the atmosphere, it might actually bend and come back to antenna on the receiving end. Or as it goes through the atmosphere, it might bend and not get to the receiving end, if you will. We could be subject to reflection. I could be reflecting off of, they show like the top of a building over here. And again, that could be positive, but it could be reflecting off a building and maybe reflecting away from where I'm trying to go, or it might be reflecting to where I'm trying to go. And this is where I'm going to use the picture from the book now too. I might reflect off the ceiling and actually propagate down the hall, if you will, to another device down the hall. That could actually be a helpful thing in some cases. Could be subject to scattering. If you have satellite TV, most people know this. Satellite TV, if you have like a rainy day or a snowy day, usually your signal gets weaker. Sometimes you might lose your signal because that satellite signal coming through all those rain droplets and snow, as the signal comes through those rain droplets and snowflakes, it literally scatters and weakens the signal. So some people with satellite TV on those rainy, snowy days, their signal is weak or sometimes can go out. Here it shows you scattering off of plant leaves and that sort of thing in a building. Diffraction. This is actually a really good picture here. It is possible where you have an antenna on this side and a receiver on this side over here that the actual hilltop actually kind of like breaks it into pieces and gets it to go over the mountain and be received on the other side. That can actually be in some cases be helpful. But as we hit objects, here we show hitting like the edge of a table, the signal hits the edge of the table and breaks into pieces. That might now make it too weak for this individual over here to receive it. And multipath signals. Now, multipath signals, in the case of here, it might actually be helpful to be able to bounce it off things and again, get it down the hallway to somebody that might not have received it before. But I might also now have an issue of one signal gets there first and then the echo, if you will, gets there second. So the receiver's like, oh, what's going on? So it can help get the signal to the destination, but it also might cause some errors because of the delays and so forth. So your multipath signals can actually be helpful, but can also cause a little bit of problem with signals too. And that brings us to our standards. That'll be a good spot to pick up on the next podcast.